I'm not sure. I'm afraid we need to use math.
This is lesson 1.8, combinations of functions and composite functions. And so today we're going to talk about the arithmetic of functions. Add, subtract, multiply, divide, and also, hopefully, compositions as well. So arithmetic combinations are particularly not difficult. When we talk about a sum, difference, product, or quotient, the sum simply means adding two functions together. What you need to be familiar with is the notation of how this works. So let's go ahead and zoom in here. Okay, so when you add two functions together, this is a notation you need to be familiar with. F plus g in parentheses, and then x in parentheses, which can also be written as f of x plus g of x. Difference notation is f minus g in parentheses, followed by x, or f of x minus g of x. Product notation, which I'm going to tell you right now, could also look like compositions. That's something in this lesson I want to distinguish between. So let's just look at this right now. F times g of x can be written as f of x times g of x. And then when you have the quotient, f divided by g of x, you have to throw in an extra condition, because remember, we're not allowed to divide by 0. So whenever you have a quotient, you have to throw in this extra condition here. G of x cannot be 0. Otherwise, you'd be dividing by 0, and that would be undefined. Now, adding two functions, given f of x equals this and g of x equals this, find f plus g. Well, it's just a matter of adding the two functions together and then using your algebra to combine like terms. So if we add the two together, we get x squared plus 4x. That's not hard. Again, the first part of this lesson that might be a little bit not difficult but unfamiliar to you is the notation. So for example, if I say f plus g of 3, what I'm doing is I'm plugging in 3 into the result. So 3 squared plus 4 times 3 is 21. Go ahead and pause the video, and now I'd like you to try exercise 9A. All right, let's move on. So find the difference of two functions. So the same functions we're looking at right now, and we're going to take the difference, f minus g. So we take the two functions and subtract them. And here's the first place that students typically make mistakes. When you're subtracting two functions, you need to make sure that you parenthesize both of them, because you're going to end up distributing a negative into the second set of parentheses. So when you do that, the algebra is the same. So you're going to get negative x squared plus 2. And then when x equals 2, the value of the difference is f minus g of 2. So the 2 gets plugged into this expression, and so we get negative 2 squared plus 2, which is negative 2. All right, go ahead and pause the video, and I want you to try exercise 9B. All right, the product of two functions, f times g. So here's f of x, here's g of x. First, let's find f times g, and then let's evaluate the product when x is 4. So f times g becomes x squared times x minus 3. So we're going to distribute the x squared, and we get x cubed minus 3x squared. Take f times g of 4, and we plug that 4 into the end result. 4 cubed minus 3 times 4 squared, which is 16. And now I would like you to pause the video and try exercise 9C. All right. Quotient of two functions. Find f divided by g and g divided by f for the given functions. Then find the domains of f divided by g and g divided by f. So, okay, first let's do f divided by g. F divided by g is f of x over g of x, which is square root of x over square root of 4 minus x squared. The quotient of g and f is this. G over f of x is equal to g of x over f of x, which is the square root of 4 minus x squared over the square root of x. Now, what is the domain of f? Well, the domain of f has to be all numbers that you're allowed to plug in. And this is going to require some thinking, okay? So what can you plug in? Well, it turns out that the only numbers that you can plug in are 0 and then all the positive numbers after that. But only until you get to 2. And you can't include 2 for the final quotient. So 0, and you can include 0, up to the number 2. Now the reason why you can't include 2 is because what is 2 squared? Well, it's 4. And 4 minus 4 is 0, and the square root of 0 is 0, and we can't divide by 0. You might ask yourself, well, why can't I plug in a number like -1? Wouldn't the denominator be positive? The answer is yes, the denominator would be positive, but not the numerator. You'd have imaginary number up here. So the domain of f divided by g is going to be 0 including, that's why I put a bracket, up to 2 not including. Looking at the denominator, what I can't have in the denominator is 0. I can have 2 in the numerator, but I can't have anything less than 0. So the domain of g divided by f is 0, not including, up to 2, including. Now go ahead and pause the video, and I want you to try exercise 9D. All right, moving on. Eventually. Hello, the internet. Behold the speed of the internet. Hey, there we go. Okay, composition of functions. Another way of combining two functions is to form what we call a composition of one with the other. For instance, if f of x is equal to x squared and g of x is equal to x plus 1, the composition of f with g looks like this, placing function g into function f. So this becomes f of x plus 1, and since f is the squaring function, what we're going to do is we're going to square the input, x plus 1. And so this composition is denoted as f open circle, that's the composition dot, g. And when you read it as f composed with g. Let's look at a picture. So the way a composition works, if you take an input x and plug it into g, it goes into this set right here, which is the range of g. But then you take that value, plug it into f, and it goes to this set right here, which is the range of f. A composition will completely bypass the middle set, and it will go straight from this part right here, the domain of g, into the range of f. And so the way we define a composition is the composition of the function f with function g is written like this, f composed with g of x, which can also be written as f of g of x. The domain of the composition is the set of all x in the domain of g such that g of x is in the domain of f. That'll take some explanation. So let's go ahead and do some examples. Part A, given that f is this and g is this, let's find f of g of x, then let's find g of f of x, and then let's find g of f of -2, a specific point. So okay, f of g of x looks like this, plugging g into f. Replace g of x with 4 minus x squared. Then, since f is just a linear function, x plus 2, you're going to turn this into 4 minus x squared plus 2. then you combine like terms, and you get the following. So that's the end result of f composed with g of x. Now let's do the composition of g of f of x. Taking f and plugging it into g, replace f with x plus 2. Then g is 4 minus x squared. So we replace the x in the x squared with x plus 2. And this becomes 4 minus x plus 2 squared. Now we FOIL this out, and we get 4 minus x squared plus 4x plus 4. Distribute the negative, and then combine like terms, and that's the end result of g of f of x. Now notice something. The result we got for f of g of x and the result we got for g of f of x are completely different. They're not the same. Part C, we're going to evaluate. We're going to plug in negative 2 into the g of f of x. Negative 2 is in the domain of g. Negative 2 is in the domain of f. So is f of negative 2 in the domain of g? Well, we plug negative 2 in the final result. Negative, parenthesis, negative 2 squared minus 4 times negative 2. Our final answer is 4. Go ahead and pause the video, and I'd like you to try exercise 37. All right, moving on. Waiting for the internet. Finding the domain of a composition. So, find the domain of f of g of x for the functions given by f of x equals x squared minus 9 and g of x equals the square root of 9 minus x squared. There's several different ways we can do this, and I want to teach you both. You're going to need to know how to do both. First way is the algebraic solution. So we do the composition. We plug g into f, and so we get f of the square root of 9 minus x squared. But f is the squaring function minus 9, so we square that component, and we get 9 minus x squared minus 9, so the end result is negative x squared. Now from this, it might appear that the domain of the composition is the set of all real numbers. But that's a false belief. That's not true. Because the domain of f is the set of all real numbers, and the domain of g only goes from negative 3 to 3. So if I go back to g of x, the domain of g is very important here. G can only go from negative 3 to 3. And so remember, I can only plug in numbers from negative 3 to 3 into the final result. Because if I can't plug them into g, then I can't plug them into f of g. And so the final domain, even though this is negative x squared, the final domain is just negative 3 to 3. Okay, there's also a numerical way that we can look at this result right here. Graphical solution. You can use a graphing utility to graph the composition of the functions, f of g of x. Set y equal to the square root of 9 minus x squared inside a square minus 9. Enter the functions as follows. y1 is 9 minus x squared in a square root, and then y2 will be y1 squared minus 9. Graph y2 only, and then use the trace feature to determine the x-coordinates of points on the graph. And you'll see that they only extend to negative 3 and to 3. So the calculator will find the domain for you there. You'll have to know both. In examples 5 and 6, we formed a composition of two given functions. In calculus, it's going to be very important to be able to identify two functions that make up a given composition. For instance, the function h, given by h of x equals 3x minus 5 quantity cubed, is the composition of f with g, where f is the cubing function, and g of x is a linear equation, 3x minus 5. So therefore, we can write h of x as 3x minus 5 quantity cubed, which is g of x cubed, which is f of g of x. So basically, to decompose a composite function, look for an inner function and an outer function. In the function h above, g of x equals 3x minus 5 was the inner, and f of x equals x cubed was the outer. So let's talk about decomposing a function. Let's write the function h of x, 1 over x minus 2 quantity squared, as the composition of two functions. Solution. One way to write h as the composition of two functions is to take the inner function to be g of x equals x minus 2, and the outer function to be 1 over x squared, which, remember from algebra, can be written as x to the negative 2 power. Then you can write the following. H of x equals 1 over x minus 2 squared, which is the same as x minus 2 raised to the negative 2, which is f of x minus 2, which is f composed with g of x. All right, go ahead and pause the video and try exercise 53. Bacteria count. Example 8. The number n of bacteria in a refrigerated food is given by the following model. N of t equals 20t squared minus 80t plus 500, and t is between 2 and 14, where capital T is the temperature of the food in degrees Celsius. When the food is removed from the refrigerator, the temperature of the food is given by the following. Temperature is 4t plus 2, but notice it's lowercase t, and t is time, where time is in hours. Find the composition of n of cap T of little t, and interpret its meaning in context. And then B, find the time when the bacteria count reaches 2,000. Okay, so first we're required to do the composition. So n of cap T is equal to 20, 4t plus 2 quantity squared, minus 80, 4t plus 2, plus 500. FOIL out the 4t plus 2 quantity squared and get the following. Distribute the other numbers, negative 80, and then combine all your like terms. The final answer is 320t squared, little t for time and hours, plus 420. So the composition function, n of t, we're putting it in context now, represents the number of bacteria in food, that's the capital N, as a function of the amount of time the food has been out of the refrigerator. Before, originally, this was the number of bacteria as a function of temperature, Celsius. That's how you interpret this. But now that we've done the composition, this is now the bacteria count as a function of no longer temperature, but time. Part B, the bacteria count will reach 2,000 when the expression 320t squared plus 420 is 2,000. When we solve this equation, we find that it's about 2.2 hours. When you solve this equation, note that the negative value is rejected because a negative time doesn't make sense. All right, go ahead and try exercise 73, pause the video, and then resume it when you're finished. Analyzing arithmetic combinations of functions. Use the graphs, I'm going to zoom out just a little bit here. Use the graphs of f and f plus g in the figure, 1.92, to make a table showing the values of g of x when x equals 1, 2, 3, 4, 5, and 6. And then explain your reasoning. So here's f plus g. Well, let's look at this ordered pair right here. This was at 1, 5. 1, 5 after you have f plus g is still 1, 5, which means that g of x had to be at 1, 0, because 0 plus 5 is still 5. This value is 2, 4, which after addition jumps up to 2, 5. What plus 4 is 5? Well, 1. Which means g of x at 2 was at the ordered pair 2, 1. And you keep following this reasoning. Let's just do one more. Notice f is at 3, 2. But then in the next picture, after addition, it becomes 3, 4. Well, okay, 2 plus what number is 4? 2. And so that means that g was at 3, 2. And you keep following that logic. So use the graphs of f and f minus h in figure 1.92 to make a table showing the values of h of x when x is the following numbers. And so you're going to use the same reasoning here, except it's going to be subtraction. And that is the lesson. I hope this was helpful. God bless you, wherever you are today.
Sweet God, from whom all blessings flow. Praise